This is on Coruscant, and this train looked uncomfortably fast to me. This train right here. So I put these timers here.
Very cool.
I wanted to get the speed so I can get the acceleration of the train when it goes around this corner, which looked uncomfortably fast to me. So I put these timers.
You're talking about angular acceleration, not going forward faster. You're talking about the turn.
Talking about the turn.
How fast?
Yeah.
Okay. I'm with you.
So if I'm sitting in a passenger seat in this, I get thrown to a side laterally. How much acceleration do I feel thrown to the wall or the side of my chair? That's what.
Oh
felt
yeah, that is
uncomfortable
pretty
to me.
fast.
Yeah, if we look at it here, if we look at how fast this goes around the corner here, let's watch it. Looks fast.
like if I'm on my phone, my head's hitting the wall.
I think so. So I want to do some calculations on this. So
Okay.
I use this angle here to get the speed.
Okay.
So I timed it when the front enters here, and then when the front leaves here to get the speed. So enters, leaves, and we get this delta t of the time.
Oh, I see. You started at 279. Is that okay?
Yeah. So I didn't try to time the zero directly with it when it enters. I was like, just throw a stopwatch up there. And whenever the frame, we can go frame by frame here. Let's see, go frame by frame.
I see what you're doing. Okay.
Yeah, right when it enters, that's when this timer starts. Then we continue.
The start time.
Yeah. And then when it exits, then that's the X. So it traversed this distance in this time.
I see.
And
The absolute time doesn't matter. It's the difference in time. Okay, I'm with you.
That's right, yeah. Difference in time, yeah. And then we get the distance traveled in that difference in time. We can estimate because we have people. And I think we said about 1 meter per one of these blocks. We counted them up.
Yeah, it's
So
reasonable.
it's about 30 meters in this time to get the speed.
I mean, if that's the size of people down there, then those blocks are, about, okay.
About a meter.
Yeah.
And then to go around this turn, when the front enters the turn, that's when this front enter goes off.
Mm-hmm.
And then when the front exits the turn, which is about right there.
I see.
Right there. That's about the time in the turn. And I estimated this is about a 30-degree situation. I'm not sure.
Yeah,
Hard to see.
Hard to see, but I mean, it's not like a 90-degree turn. It's got to be a lot less than
90-degree
that.
turn.
Yeah.
Probably the max it is 45 degrees, which would be even harsher. So if we bring it down to 30 degrees, that's going to... We'll see if at 30 degrees, at the speed we calculate, is it a comfortable acceleration? Let's find out. So we've got our delta t's, and this gives us enough information to calculate the acceleration. Okay. So we'll use this picture later. Here's the first calculation. The speed. So the speed is delta x over delta t.
Cool.
We said there's about 30 blocks. Go ahead.
Change in distance over change in time. Yep. I'm with you.
Yep. And so there's about 30 of those blocks for about 1 meter per block. So that's the distance traveled. This was the delta t. So we got 30 meters per 0.84 seconds, which is about 36 meters per second. Okay.
Quick train, but I mean, Star Wars. Okay.
Yeah. And then in order to get the acceleration, we need to find this radius of the turn. So this is about a 30-degree turn.
Okay. So the train is going from the bottom left of that blue arc to the top right. It's doing its like right-hand turn. Okay. I'm with you.
Yep. And that's this turn right here, back here.
Yeah. Okay. Yeah.
So we don't know the radius of the turn, but we estimated the angle to be 30 degrees, and we can estimate the arc length by speed times time. So let's do that. So the angle is 30 degrees. That's arc length over radius. We want to find the radius, so we flip these two. This. Arc length is v times time divided by the angle.
It's the distance traveled. Yeah.
Yep. So it's 36 meters per second times 0.62 seconds in the curve, which came from the video.
Turn. Yep.
Divided by 30 degrees, which is pi over 6 radians.
Yep.
Gives us 42 meters for the radius.
Okay, sure.
It's a tight turn, I think. And then we can put it all together for the turn acceleration, which is v squared over r for circular motion. Gosh, the physics of this, we just got to pull this equation from a book.
I mean, that's what it is, yeah.
So we got 36 meters per second squared. That's the v we estimated, divided by the radius. Gives us 30 meters per second squared, or 3g laterally.
3G turn.
Whew.
Okay, wait. What does that mean? That's so you feel your body feels 3 times as heavy as normal, if it was like up and down.
Yep.
So I'm trying to like what is 3G? I'm not a pilot. So I guess roller coasters.
Okay.
I think roller coasters, if you're upside down, you can get -1G, and then in like the most swoopy part as possible.
Mm-hmm.
Yeah. So 4G, the highest ones.
I believe it's Shockwave at Six Flags Texas pulls something like 6Gs.
Cool. 6Gs. So 6Gs is like, if you've been to this particular roller coaster, then you know what that 6Gs feels like. So then I guess half of that. I think caveat though is that 6Gs in line with your body, like lined up and down, feels pretty okay, because I mean it's a lot of force, but also your body is designed to handle G forces that are up and down. Sideways is a different story.
Yeah. So going around this turn, you're going to feel flung to the outside of the turn by 3Gs. That seems like a lot.
I mean, even when you're turning in your car with significantly less than 3Gs, like you feel it. You feel like you're getting pushed to the window, because your body and the shape of the chair is not designed for lateral Gs. So I wonder, did all these people in this train, do they need helmets? Did they get their heads slammed against the window?
Oh gosh, no way, because it's a commuter train. Which okay, hold on. In Mandalorian, we saw Bo-Katan and the Mando in a train. I remember they were like whipping around these turns, and they didn't feel anything inside. Which means there's some kind of weird like inertia tech in Star Wars.
That's true. Yeah, because otherwise, every time they jumped at light speed, everyone should be smeared against the wall, like just splashed, like gushy, gross.
Right. So maybe internal to this train, once the doors close, the
some type
inertia
of force
tech
field
turns on.
Something. Yeah.
And they fly around curves and accelerate at deadly speeds because it doesn't matter anymore. Okay.
Cool way to make Coruscant compact. Otherwise, these trains would have to have these big, sweeping, gentle turns. Like Coruscant's tight.
I'm also glad that my intuition about this being like, uncomfortably fast was kind of right. Kind of happy about
3Gs.
that.
3Gs. Like imagine jumping up and down and like you can shock absorb with your legs, but imagine jumping up and down, but then landing in a side plank. Like your body's not made for that. Can't do that.
Yeah, no way.